Hello everyone and welcome back to this course on discrete mathematics. As we are at the final part of this set, part 3. What's going to be part of this session? Here is the outline of today's lecture. In this part, we are going to look at some set identities, proofs, and how computer representations can be made. We'll talk about on Russell's paradox as well as the halting problem. Coming to some of the identities that we have here, a set identities are basic law on how set operates. So let's see, like for example, you have logical equivalence that we have seen earlier in the Boolean logics. So with regards to that, we are going to touch some of the topics that we have seen earlier, and we are going to relate that with that of a set theory. Of course, George Boolean or the things that have been developed by other mathematicians never thought that their area or their research or their contribution in one area might be used in other areas. But today we see that all these things can be applied to other fields and how they are complementary to one another. Say for example, you can replace the union with for all operations, the quantifiers, or you can also use the symbol intersection for AND operation. In fact, union is like OR operation, and intersection is like AND operation, and empty set is like the fallacy. In other words, it's like we have negation law, the NOT operation, you can say the NOT operation, null set, and the universal set is like the tautology T, it's like true and false. Well, you can still think about what De Morgan came up with, and we are going to use that here as well. A intersection B, the whole complement, is equal to A complement union B complement. Again, A union B, the whole complement, is equal to A complement intersection B complement. Can you relate that with that of AND OR logics? Well, let's see whether we can prove the set identities. For example, A intersection B equals B minus A. So now we have 4 methods to prove the set identities. We'll see one by one. The first one is the basic set identities. The second is membership tables. The third one is we can prove each set is a subset of each other. So this is like proving 2 numbers are equal by showing that each is less than or equal to another number. And we can also use the builder notations and logical equivalence. It's one of the famous way to prove the set identities. So here is one way. You can see how we can also represent by means of the Venn diagram. A intersection B equals B minus A. For example, we know that what is A intersection B? It's a common term between A and B. That's in the center. We have A intersection B. Then if you talk about B minus A, that is the part of B that is not in A, and now you have B minus A. So that is this common term L. Well, we can see here it's clearly B minus A is equal to A intersection B. Isn't it easy to prove this way? Well, it's easy for us to understand as well when you see things which are represented by means of pictures. Let's try to use some basic set identities to prove it. So A intersection B can be written as, from the above, we are trying to prove it. So A intersection B equals B minus B intersection A complement. so that we use this from the definition of differences. Then comes, again we are trying to use the difference definition, so you can recall the difference definitions there. Again, B minus B intersection A complement can be written as B intersection B intersection A complement the whole complement. So you can see the double complement coming there, and when you take this complement inside, so it comes to be like B intersection B complement union A double complement. That's by means of De Morgan's law. Again, you can know that from complementation law a double negation will cancel it off, so double negation of A is A. Then you can write using distributive law B intersection B complement union B intersection A. Now what is B intersection B complement? Does it sounds like some law that you have seen earlier? Yes, of course, that's a part of the complement law that yields you the empty set. So empty set is equal to B intersection B complement here. So we have empty set union B intersection A. Therefore, finally you have the identity law. We can simply write B intersection A union with the empty set is B intersection A, and again B intersection A is equal to A intersection B, that is commutative law. This is one of the basic set identities in which you can follow the steps and prove it. Well, we do have certain problems like this to come, at least for your assignments as well as some homeworks that if you like to do, you can try out these problems. It's quite interesting because we just use the logic proofs as well as the identities and the laws and try to manipulate so that we can try to see whether we could prove it or not. And at times, if there are times that you can't prove it, which means that, well, they are not equal, that's it. Here we just proved that it is equal. And other way is the membership table. So here you can see it shows all combination of sets as an element. Okay, you can see that here 1 means the element belongs and 0 means it does not belongs. So we will see we have A, B, A union B, A intersection B, A minus B. So when A is 1, which means that the 1 means the element belongs and 0 means it does not belong. So we have A1, B1, A union B is 1, A intersection B is 1 and A minus B is 0, just you are taking the element out. And when A is 1 and B is 0, A union B is 0, in fact A union B is 1, A intersection B is 0 and A minus B is 1. Can you recall this relation with that of OR and AND gate? Yes, it's very similar, isn't it? So this is like the OR operation and this is like the AND operation, OR and AND operations, just for your reference. So that's how we follow through. So the top row is all elements that belong to set A and B. Thus all these elements are in union with an intersection but not difference. As you can see here, the first row we had union, we had intersection, but it's not. A minus B is going to be 0. And again A is 1 and B is 0. At that time you have 1 because A minus 1 is A minus 0 is 1 there. Again the second row has been explained here well. So thus these elements are in union and the difference but not the intersection there. So you can see step by step all these rows represent various properties that we have just seen. Thus these elements are thus either union, intersection, or difference, because all are 0. So we can use this membership and try to use the same way to prove it. Here you have A intersection B equals B minus A. So because we have two indicated columns here in the shaded portion of these columns, A intersection B and B minus A intersection B, and these expressions, they are identical and they are very similar to the Boolean logics that we have seen before. So here the proof by showing each set is a subset of another one. Assume that an element is a member of one of the identities, then show it is a member of other. Repeat for other identities. How do we do that? We will try to show it. For example, X is an element of A intersection B. This implies that X is an element of B minus A, and X is an element of B minus A implies that X is an element of A intersection B, biconditional. Yes, this is biconditional. So it's not good for long proof, as you can see through, like you get confused as it goes long. So it is okay for us to prove this way with a simple proofs like that we have here. So here we assume that X is an element of B minus A. So by definition we know that X is an element of B and X is not an element of B minus A. So then now if X is an element of B minus A, then by definition of difference X is an element of B but it is not an element of A. Since X is not an element of B minus A, then only one of the inverse can be true, right? So that's because of the De Morgan's law. We say X is an element of A or X is an element of B. In other words, X is not an element of B or X is an element of A. So we have two things here. One is, by definition of difference, we can see that X is an element of B, the first part, when you take the whole thing here, and X is not an element of B minus A. But when you take this B minus A itself, the second part B minus A itself, you can see X is element of B and X is not an element of A. That is again definition of the difference definition. Since we know that from the first X is not an element of B minus A, then only one of this inverses has to be true. So either X is not an element of B or X is an element of A. So we have that X is an element of B and X is not an element of B or X is an element of A. So it cannot be the case where X is an element of B and X is not an element of B. So that we want to exclude that, in which we have the remaining one is X is an element of B and X is an element of A. What is this property in which X is common for both the set A and B? Well, that is the definition of intersection. Yes, we have reached this conclusion by proving by means of this subset idea. Yes, if X is element of B minus A, then X is element of A intersection B. Let us see more on this subset. X is element of A intersection B. By definition of intersection, we have A is an element of, X is an element of A as well as X is an element of B. So that is the definition of intersection. It has to be part of both. So thus we know that X is not an element of B minus A. We know B minus A includes all elements in B that are also not in A and not include any elements of A. So that is the basic definition of difference. So that's why we can say that it has all elements of B that are not in A. So that's why we call it as B minus A. So let's consider B minus A. We know that X is not an element of B minus A, and we know that if X is element of A intersection B, then X is element of B as well as X is element of A. So let's take X is element of B by definition of intersection. Thus, if X is element of B and X is not an element of B minus A, so we can restate using the definition of difference that X is an element of B minus A. Yes, that's how we coming to this common ground of using the subset and trying to prove these set identities. So thus, if X is an element of A intersection B, then X is an element of B minus A. So this is quite good for us to think about, because these identities can really help us to contemplate more on the logics of sets. Let's try to use the builder notation and logical equivalence. First, translate both sides of the set identities into set builder notions. Then message one side or both sides to make it identical to others. So do this using logical equivalence. Let's try. B minus A is the original statement that we had. Then we could say that the definition of difference for all x such that x is an element of B and x is not an element of B minus A. So let's use the negating elements here. So x for all x is an element of B and negation of x is an element of B minus A, because we have taken negation outside. Let's see again using the difference definition. We have x is an element of B and x is not an element of A. Again we can see here we can use the De Morgan's law, by which you are in fact eliminating the negation outside. So x is not an element of B or x is element of A. So what we have done is we have taken the negation out and we have replaced the AND with OR, as well as the definition of this thing, x is element of B has been changed to x is not an element of B, and x is element of A has been changed to x is an element of A. And by distributive law we can say x is element of B and x is not element of B, or x is element of B and x is element of A. Again using the negation property there. So we take negation there out. So negation of x is element of B is given here. And again you can see we are using the negation rule there. So since x is element of B and negation of x is element of B is there, so since we have negation, every time it would be false, every time. In other words, every time that set becomes empty. So we say F, say for false, or x is element of B and x is element of A. Yes, we are drawing to the conclusion soon. So then now we remove the F, because we are not interested in F, we want to be true. So this part, x is element of B and x is element of A should be the true part. That is the identity law. Yes, that is the property of definition of intersection, which is common for A and B. Definition of intersection of A and B. So sometimes we like to prove it the other way. but at times it may be annoying. If it's a simple statement, it would be easy. Say this is quite simple, but you can try it out. Why don't you try to prove it out? Let's see some points on computer representation of sets. Assume that U is finite and reasonable, and let's say U is be the alphabets. Each bit represent whether the element in U is in the set. Say for example, you have the set of elements there. So U is A, B, C till Z, and we represent the vowels by means of 1. You can see here A, E, I, O, U. Only those parts we have 1, the other parts are 0. So it's a simple way to represent. The computer can understand. For example, if you want to represent the constants except vowels, all other things, just A, E, I, O, U are zeros and other things are 1. So let's consider more here. If you want to do the union part of these two sets, a set of vowels and set of consonants, well, this is what you get if you take the union. If you take the intersection, the OR, you get this one. So initially for union you get all ones, and for intersection you get all zeros. So which means that we can do a lot of manipulations using sets in computer as well. So there are a few more problems that you can think of. Here is some examples. Let A and B and C be sets shown here. Why don't you try these problems in class or in your free time? Why don't you see whether you could be able to follow through these problems about subsets? Yes, it's good for you to work out. We have already seen few problems on how to work out with these kind of things. Let's talk about the Russell's paradox now. It's one of the interesting paradox, and you can see how it is related to our sets that we are discussing today. Consider the set S equals for all A such that A is a set and A is not an element of A. How could that be? Is S an element of itself? Let's consider S is an element of S, then S cannot be in itself by definition. Well, if you could see if S is not an element, then S is in itself by definition. So there is a contradiction. In order to help us understand this point of this contradiction, let's consider the set. Again the same definition, S equals A such that A is a set and A is not an element. So this is an issue in the set theory. It's a kind of a paradox that has been developed. We call this as Russell's paradox, and one of the famous way to understand this is like say for example a barber. There is a barber. So there is a barber, the one who shaves all those and those only who do not shave themselves. So he is going to help shave everyone, and he do not, I mean, this barber definition, just let's say an example, let's say a scenario here. For example, there is a city, and in this city all men have, say, beards, and then there is this barber in the city, and he shaves everyone who does not shave themselves. Okay? So the question is, does the barber shave himself? If you think about the answer to this question, you will come up with the contradiction. So that's the Russell's paradox. It's like the barber cannot shave himself, as he only shaves those who do not shave themselves. As such, if he shaves himself, he ceases to be the barber. Conversely, if the barber does not shave himself, then he fits into the group of people who would be shaved by the barber. So thus, as a barber, he must shave himself. Can you see the contradiction there? So the question initially I asked is, in the city, the barber shaves everyone who does not shave themselves. So the barber cannot shave himself, as he only shaves those who do not shave themselves. So if he shave himself, he ceases to be a barber. The same thing, we have the converse idea. If the barber does not shave himself, then he become a part of people who does not shave, and he would be shaved by the barber. Yeah, thus the barber must shave himself. So there is a contradiction that you see. That is kind of Russell's paradox. In other words, this paradox can also be stated by means of sets that we have seen here. So there can be no set which contains all sets. There are some sets that cannot be part of all sets, you could say. There can be no sets which contains all sets, because if there are such a set, and it must contain itself, but if it contains itself, it's impossible to prove that it's a part of other sets as well. So this is a contradiction that was created, and this rose a lot of interest in the research of not only set, even in other areas of logics and contradictions. So let's see more information about other contradiction that came along. So if set does not contain itself, we would be wondering how this would fit the definition. Like here we have S, for example, equals, for example, A, such that A, you could also say that A is a subset of the union, and A is not an element of A. So we could say S is an element of S implies S is not an element of S. Same thing, S is not an element of S implies S is an element of S. So the conclusion, we have a contradiction according to the Russell's paradox. Restrict set theory to not include set which are subset of themselves. So that's one way of solving it. And here's another problem that we have, that is called the halting problem. So this is this has a long history, in fact. So well before the actual construction of the electronic computers, we had to perform certain operations and logics. Of course, if you closely examine this problem, they are kind of little bit similar and related to the Russell's paradox. So given a program P and input I, will the program P ever terminates? Meaning, will P of I loop forever or halt? Can a computer program determine this? So that's hard for us to say. Can a human? So yeah, this was first shown by Alan Turing. So if you have some experience in programming computers, you know how badly an infinite loop can damage your whole project. Well, let's see some points here. To solve a halting problem means we create a function halt check P comma I. P is the program we are checking for halting, and I is the input to that program, and it will return loop forever or halts. So note it must work for any program, not just some program. Yeah. So it's better if you put this halt check. Let's see. Can human determine if a program halts? Given a program of 10 lines or less, can a human determine if it halts? Assume no tricks, the program is completely understandable, and assume the computer works properly, of course. So we ignore the fact that an int will max out 4 billion. Let's say, for example, let me briefly tell you simple way in which something can be in a loop forever. Say for example you have function 1. And you have lines here, and then you're calling function 2 here. Then you have function 2 here. Here you are calling function 1. So as you can see, the line of codes are executed and it goes to function 2. So the function 2 starts its execution. As it executes, it goes to function 1. So it goes to this part. From here to here, it starts execute. Then when it reaches this part, it goes to function 2. Its kind of infinite loop is created where it's hard for us to determine when this would halt. Well, here is a simple halting test. Print Alan Turing was a genius. Function halt test 2 for factor from 1 to 10, print factor, and function halt text 3 while true, print hello world. Function test halt 4 for int I equals 10, x is greater than 0, print hello world, x is equal to x plus 1. Well, we are expecting things to happen to have different, for example, here we have the while loop which are required for 10 times as well. So there are a few things that we can think about how this would work. So perfect numbers, and numbers whose divisor not including the number add up to the number. For example, 6 equals 1 plus 2 plus 3. You know, 1 is the divisor of 6, 2 is the divisor of 6, 3 is the divisor of 6. So they add up to the same number 6, 1 plus 2 plus 3. 28, 1, 2, 4, 7, 14, they are all the divisor of 28, but when you add these things, it yields you 28. That's the perfect number. Okay, question is list of first 10 perfect numbers. Oops, it seems so large numbers you have. Now you can see the last one is 54 digits. Can you imagine? All known perfect numbers are even. It's an open, unsolved problem that we have here. Problem if odd perfect number exists. Do we really have a odd perfect numbers? You can challenge yourself if you want. So you can also refer some sequences and see if you like to work on that. So odd perfect number search, if you like, you can see simple codes are given here. You could use it for finding out the odd perfect numbers. Just a simple loop. Now the question is, will this program ever halt? Because you are trying to find an odd perfect number. You are trying and trying and trying and trying. It goes on and on and on. where does it leave us? The question here. If a human can't figure out how to do halting program, we can't make a computer do it for us. Therefore, it turns out that it is impossible to write such a halt function. But how do we prove this? And halt check non-exists, like consider program I, a program P of I, you have P and I, and you are trying to see the halt check of P comma I exist, tests if P of I will ever halt or is going to have a loop forever. A program is a series of bits, we know that, and thus can be considered as data as well. Thus we can see, can check halt P comma P works. It's using bytes of program P as the input to program P. So consider a new function here, test P, loop forever, and text halt you have, and you can see halts if check halt P comma P prints loop forever. So you are trying to see whether you are going to halt it. Do we agree that test function is a valid function? And how long are you going to wait? That's another question, right? Before a loop is going to ever start. If test of test halts, if test of test goes for loop forever. So if it halts, then return loops forever, which means test of test loop forever, then you have a contradiction there. But if it goes to loops forever, you're going to return halts, and then again, which means test of test is halts, and then there is a contradiction. This kind of things can happen. Why do we care about the halting program then? It's because the first algorithm was shown not be able to exist, and you can prove an extension by showing examples a correct program, but it must be harder to prove that a program can never exist. So let's see, just before I finish, I want to tell how these halting programs are managed in many different places. For example, in electronics circuits, there are certain thing called a watchdog timer. Of course, when assembly language programming is made, and we want to make sure that a system does not get stuck in some area or goes to an infinite loop. So a watchdog timer, it's called a watchdog timer, is used, and it checks if the system or if the program doesn't halt within a given frame of time. If it does halt within the frame of time, it's fine. If it does not halt, then the watchdog timer waits for a certain time and then it triggers a reset kind of thing. Anyway, that is not the goal of actual thing that we are talking about, but I just want to imply that in electronics we have this system to halt a system, but actual halting problem is quite a serious thing. In other words, people are working still on finding a solution to this problem. For example, as we know, can we ever find a perfect odd number? And when you are going to halt the program if you start to run the program today? That's an interesting question. Just try to contemplate on these thoughts as we discussed about the sets and its application today. And I'm looking forward to see you next time. And we are going to talk about inductions, functions, and so on in the coming lectures. Until then, goodbye. Have a nice time.